NASA's Perseverance rover has once again revolutionized our understanding of Mars with an extraordinary geological find that has left scientists both amazed and perplexed. While conducting its meticulous exploration along the rugged rim of Jezero Crater, a site carefully selected for its potential to reveal secrets about Mars's watery past, the rover's sophisticated imaging systems detected a bizarre rock formation unlike anything previously documented on the red planet. This remarkable discovery consists of a dark gray, weathered rock surface, absolutely blanketed, with hundreds of perfectly spherical and near-spherical structures ranging in size from barely visible specks to about 3 millimeters in diameter, creating a texture that appears almost manufactured rather than naturally occurring. The rover's high-resolution cameras captured these peculiar features in stunning detail, revealing not just their uniform distribution across the rock face, but also their uncanny geometric precision, with many spheres showing near-perfect circularity, while others display slightly elliptical or irregular shapes, all embedded in a matrix of finer-grained material that presents its own set of mysteries for planetary geologists to unravel. NASA's Perseverance rover makes stunning discovery. The rock containing these mysterious spherical formations has been officially designated St. Paul's Bay by NASA's science team, continuing the mission's tradition of giving evocative names to significant geological finds that help researchers remember and discuss specific targets of interest. On closer examination using Perseverance's suite of advanced imaging tools, researchers observed that the rock's surface is densely packed with these peculiar spherical structures, creating a texture that resembles nothing so much as a cosmic version of bubble wrap, or perhaps some alien equivalent of fish eggs. The spheres themselves exhibit a remarkably consistent dark gray coloration that contrasts sharply with the surrounding matrix material, but display surprising diversity in their physical forms. While many maintain perfect spherical symmetry that would make a geometry teacher proud, others appear slightly elongated or oval-shaped, and some show jagged, fragmented edges suggesting they may be pieces of larger spherules that fractured during some unknown geological event. Most intriguingly, numerous spheres feature what scientists are preliminarily calling pinholes, tiny, remarkably circular openings that penetrate their surfaces, creating an effect similar to the holes in a sponge or the vesicles found in certain volcanic rocks on Earth, though with some subtle differences that make direct comparison challenging. The Perseverance science team, thoroughly captivated by these bizarre and unexpected formations, has affectionately dubbed them shocking Spherules, a name that perfectly captures both the sense of surprise surrounding their discovery and the genuine astonishment they've provoked among researchers who have studied Martian geology for decades. This catchy moniker serves the important scientific purpose of clearly distinguishing these particular spherical formations from other, more familiar types found elsewhere on Mars, as their unique combination of characteristics strongly suggests they may have formed through fundamentally different geological processes than their predecessors. The discovery has ignited vigorous debate and excited discussion within the planetary science community, with experts proposing and carefully evaluating various hypotheses about their origin while being careful to avoid jumping to premature conclusions that could bias future investigation. What makes these spherules particularly shocking to experienced researchers is their unexpected combination of features: their remarkably uniform distribution across the rock's surface, their relatively consistent yet slightly varied sizes, and especially those enigmatic pinholes that currently defy straightforward explanation and may hold crucial clues about the environmental conditions present during their formation billions of years ago. Perseverance encountered this geological marvel while conducting detailed investigations at a site mission planners had designated as Broom Point, located along the western rim of Jezero Crater in an area that orbital imagery had identified as particularly promising for scientific study. This specific location was carefully selected as a high-priority target after images from spacecraft like the Mars Reconnaissance Orbiter revealed striking alternating bands of light and dark-toned rock layers that suggested complex geological processes had shaped this region over immense timescales. The rover's approach to studying Broom Point followed the mission's standard but highly effective exploration protocol, first conducting remote sensing observations from a distance using its mast-mount cameras and spectrometers, then moving in for closer examination of particularly interesting features with its arm-mount instruments, and finally selecting the most promising targets for more intensive study and potential sample collection. It was during this meticulous, multi-stage survey process that the rover's sharp-eyed cameras serendipitously spotted the spherules-covered rock, sitting inconspicuously near the primary sampling area, immediately capturing the science team's attention with its unusual texture and appearance that stood out even among the many strange formations Perseverance has documented during its mission. Just days before making this unexpected discovery, Perseverance had successfully completed one of its primary mission objectives at Broom Point by using its sophisticated robotic arm and drill system to bore into and collect a core sample from one of the lighter-colored rock layers that orbital imagery had identified as particularly interesting. This carefully planned sampling operation, which represented months of preparation and analysis by the science team, went exactly as planned, successfully securing another valuable piece of Martian geology for eventual return to Earth, where it can be studied with laboratory equipment far more powerful than anything the rover carries. As scientists were reviewing the post-sampling images to thoroughly document the drill site and its immediate surroundings, a standard procedure to create a complete contextual record for future reference, they noticed the curious, spherules-studded rock sitting nearby in what the team calls the workspace, the area immediately accessible to the rover's instruments. The fortuitous timing of this discovery, coming right after the successful completion of a major sampling milestone, has given researchers an unexpected but tremendously valuable bonus target for investigation, providing a rare opportunity to study two distinct but potentially related geological features within the same small area of Jezero Crater's rim, and perhaps uncover connections between them that could shed new light on the crater's complex history. The spherules embedded in the St. Paul's Bay rock display a fascinating variety of forms that have given planetary geologists much to ponder as they attempt to unravel the story behind these peculiar formations. Many appear as essentially perfect spheres, so geometrically precise in their circularity that they could easily be mistaken for manufactured objects at first glance, while others show more elliptical or oval profiles that suggest they may have experienced some deformation or alteration since their formation. Some spherules present angular, fragmented edges that strongly imply they may be pieces of larger spheres that broke apart, either through weathering processes over the billions of years since they formed, or perhaps during whatever geological event originally created them. The size distribution follows a relatively narrow but still significant range, with most spherules measuring between 1 millimeter in diameter and about the size of a pinhead or small bead, though careful measurement has revealed subtle variations that may prove important for understanding their formation. Their arrangement across the rock surface appears essentially random, rather than following any obvious pattern or organization into distinct layers or clusters, though detailed statistical analysis may yet reveal subtle spatial relationships not visible to casual inspection. This diverse morphology provides crucial clues about their formation history, as different geological processes tend to produce particles with characteristic shapes, size distributions, and spatial arrangements that experienced planetary geologists can recognize and interpret to reconstruct ancient environments and events. Perhaps the most baffling and scientifically intriguing aspect of these Martian spherules is the presence of tiny holes or pits in many of them, features that have become a particular focus of study and debate among the Perseverance science team. These pinholes, typically much smaller than the spherules themselves but remarkably consistent in their circular shape, appear as perfect little openings that penetrate into or sometimes completely through the spherical structures, creating an appearance somewhat reminiscent of the holes in a sponge or the dimples on a golf ball, though with important differences that make simple analogies potentially misleading. On Earth, similar features in volcanic rocks are called vesicles and form when gas bubbles become trapped in solidifying lava and then either remain as closed cavities or become open to the surface as the surrounding material continues to change. However, the Martian pinholes show some subtle but potentially significant differences from terrestrial vesicles that make direct comparison challenging. Some appear to connect to internal cavities within the spherules, while others seem to be surface features only, and their distribution varies intriguingly from one spherule to another, with some having just one central hole, others several scattered across their surfaces, and some none at all. These minute but potentially crucial details may hold the key to understanding exactly how and under what environmental conditions these peculiar formations came into existence billions of years ago, making them a primary focus of ongoing analysis by the Perseverance science team as they attempt to reconstruct the complex geological history of Jezero Crater. This remarkable discovery represents just the latest chapter in a long history of spherical formations being found on the red planet's surface, with each new find adding important pieces to the complex puzzle of Martian geological evolution. The earliest, and perhaps most famous example came in 2004, when NASA's Opportunity rover found numerous small, round concretions that scientists nicknamed blueberry due to their shape and bluish-gray hue in false color images, features that became iconic symbols of Mars exploration and our growing understanding of the planet's watery past. These hematite-rich spheres, typically 4 millimeters in diameter, were interpreted as concretions formed through mineral precipitation in water-saturated sediments billions of years ago, providing some of the most compelling early evidence that liquid water had once been abundant on Mars. Later, the Curiosity rover, which landed in Jezero Crater in 2012, observed similar but distinct spherical features in the rocks of Yellowknife Bay, though these tended to be smaller and more variable in composition than Opportunity's blueberries, suggesting possible differences in their formation environments or processes. More recently, Perseverance itself documented popcorn-like textures in sedimentary rocks at Neretva Vallis, an ancient river channel that once fed into Jezero Crater, with these features also being interpreted as concretions formed through groundwater action. Each of these prior discoveries contributed valuable pieces to our growing understanding of Martian geological history, but the new shocking Spherules appear sufficiently distinct in their characteristics to potentially rewrite parts of that story, suggesting either a previously unrecognized formation process or environmental conditions unlike those inferred from earlier finds. In nearly all previous cases of spherical formations found on Mars, scientists ultimately concluded they were observing concretions, mineral structures that form when dissolved minerals precipitate out of groundwater and accumulate in concentric layers within sedimentary rock, gradually building up around some nucleation point to form spherical or near-spherical shapes. This process, well documented on Earth in places like Utah's spectacular national parks where magnificent examples can be seen weathering out of sandstone cliffs, typically occurs over extended periods as mineral-rich water slowly percolates through porous rock, with the resulting concretions often acquiring their characteristic spherical shapes because minerals tend to precipitate uniformly outward from their starting point. On Mars, such features have been considered among the strongest evidence we have for the planet's watery past, as their formation requires not just the presence of liquid water, but its sustained action over considerable time frames to produce the observed structures. The initial assumption upon finding the new Spherules might naturally be that they represent more examples of these concretions, but several characteristics, particularly the pinholes and the diversity of shapes, suggest this explanation may not fully account for all their peculiar features, leaving room for alternative or additional formation theories that could dramatically expand our understanding of the geological processes that have shaped Mars over billions of years. While some of the spheres could indeed be concretions, others may have formed through different mechanisms, potentially recording entirely distinct chapters in Mars's complex environmental history within the same rock. One particularly compelling alternative theory suggests these spherules might be products of ancient volcanic activity on Mars, formed through processes similar to those that create various types of volcanic particles on Earth. When volcanoes erupt explosively, they can eject molten rock into the air, where it breaks up into droplets that then cool and solidify during flight, falling back to the surface as tiny spherical or tear-shaped particles, collectively called volcanic pyroclastics. On Earth, similar formations are known by evocative names like Pele's Tears, after the Hawaiian volcano goddess, when they're individual tear-shaped droplets, or accretionary lapilli, when ash particles accumulate in concentric layers around some nucleus to form larger spherical aggregates, somewhat like hailstones forming in storm clouds. The pinholes observed in many of the Martian spherules could represent gas bubbles that were trapped as the molten droplets solidified, similar to vesicles in volcanic rocks, with the holes forming either as the gas escaped or as the surrounding material later eroded to expose once hidden cavities. This explanation would carry significant implications for our understanding of Jezero Crater's history, suggesting the region experienced substantial volcanic activity that could have dramatically influenced its environment and potential habitability during Mars's early history. However, the theory still needs to account for why these spherules appear different from other known volcanic particles found elsewhere on Mars, and why they're concentrated in this particular rock formation, rather than being more widely distributed across the surface if they were indeed products of regional volcanic events. Another plausible explanation that has gained traction among some researchers involves meteorite impacts, which have played a major role in shaping Mars's surface throughout its history. When a large space rock slams into a planetary surface at tremendous speed, typically many kilometers per second, the immense energy can vaporize both the impactor itself and some of the target rock it hits, creating a superheated plume of vaporized material that expands outward before cooling and condensing. As this vapor cools, it can condense into countless tiny spherical droplets that then rain back down to form what geologists call impact spherules, particles that often contain distinctive mineralogical and chemical signatures of the extreme pressures and temperatures generated during impact events. The pinholes observed in many of the Martian spherules could theoretically result from gas escape during this rapid cooling process, similar to how bubbles form in some rapidly cooled glasses or slags. If this hypothesis proves correct, these spherules might represent compelling evidence of a major impact event in Jezero Crater's history, perhaps even the original impact that created the crater itself, making them invaluable chronological markers that could help date geological layers and reconstruct the sequence of events that shaped the area. However, impact spherules typically show more variation in size and composition than what's been observed so far in these Martian examples, leaving some scientists skeptical of this explanation. And the apparent concentration of these spherules in one specific rock rather than being distributed across a wider area presents another challenge that the impact hypothesis would need to address convincingly. Complicating the investigation is the preliminary assessment that St. Paul's Bay appears to be what geologists call a float rock, a piece of bedrock that has become detached from its original geological layer and moved to its current location, possibly through erosion, slope processes, or other surface dynamics over immense timescales. This means scientists can't immediately determine with certainty which rock layer it originally came from, or what its stratigraphic context was within the broader geological sequence of Jezero Crater's rim. Information that would be crucial for properly interpreting the spherule's significance and formation history. Float rocks present a special challenge for planetary geologists because their displaced position makes it significantly harder to connect them to the broader geological story of the area and to determine their age relative to other formations. The Perseverance team is now working diligently to trace the spherule-rich rock's possible origins by comparing its detailed composition to nearby in-place outcrops through spectroscopic analysis, examining the surrounding terrain for clues about how it might have traveled to its current location, and searching for other similar rocks that might help establish a pattern. Solving this puzzle is absolutely crucial for properly interpreting the spherule's significance within Jezero Crater's complex geological history, as their original depositional environment, whether part of a volcanic ash layer, an impact ejector blanket, or a sedimentary unit formed in water, could hold vital clues about the processes that created them and the environmental conditions that prevailed at the time. As Perseverance continues its groundbreaking mission, scientists plan to employ the rover's full suite of state-of-the-art instruments to unravel the mystery of the shocking spherules and what they can tell us about Mars's geological evolution. Detailed chemical analysis using PIXL, planetary instrument for X-ray lithochemistry, will reveal their elemental composition at extremely fine scales, potentially identifying diagnostic signatures that could point to specific formation processes, while Sherlock, scanning habitable environments with Raman and luminescence for organics and chemicals, will examine their molecular structure and search for potential organic compounds or distinctive mineral phases that might provide additional clues. High-resolution imaging using the rover's cameras will document their microscopic features in unprecedented detail, creating a three-dimensional record of their shapes, sizes, spatial relationships, and those all-important pinholes that may hold key evidence about their formation, environment. These investigations represent far more than just satisfying scientific curiosity about an odd rock. They'll contribute vital information about Mars's geological evolution and potential past habitability that could reshape our understanding of how rocky planets form and change over time. Each new discovery like this brings us closer to answering fundamental questions about whether Mars ever hosted life, what processes shaped its surface over billions of years, and how Earth's own geological history compares to that of our planetary neighbor. The shocking spherules may be small in size, but their scientific importance could be enormous as we continue piecing together the red planet's complex history, potentially revealing new chapters in the story of our solar system's evolution and the possibilities for life beyond Earth that we're only beginning to explore.
Thank you for watching. Please don't forget to like and subscribe.